to welcome Vineeth Gupta. He is an alum of our program. What cohort were you, Vineeth? 12? 11? Which one? 23. So 2 years ago. 12. Cohort 12. Cohort 12. Okay. So welcome to the Data Science Speaker Series. Vineeth is a machine learning engineer at HP, where he focuses on building privacy-preserving AI systems for on-device and edge deployments. His work sits at the intersection of machine learning, systems engineering, and real-world AI production. And today, he'll share a systems-first look at how on-device AI is built and the key trade-offs between privacy, performance, and the cloud versus edge deployment. So please join me in welcoming Vineeth.
Thank you, Elizabeth, for that great introduction. It's great being back at the university again, and nice to see you all. So today I'm going to talk about on-device AI, and we'll cover some interesting topics there. And during the session, if you have any questions, feel free to raise your hands and ask the questions. So starting with the tagline, AI is coming closer to the user. Basically, what does this line mean? So previously, we used to use AI for recommendations, for searching on web, and etc. But now, we all are using AI for researching new topics, learning concepts, and vibe coding too. So how many of you do vibe coding? Nice. That's good. So, okay, I'm curious. Let's do some question. Raise your hands and give me a word. So, how many of you have used AI to get a different perspective about some personal situation or some professional situations? Nice. Okay, so majority of the people. Okay. And how many of you have used AI as a therapist? Nice. So it's interesting to see many people are using for AI for wide range of activities. But have you ever felt hesitated to share the details with AI? Of course, how many of you feel completely comfortable to share everything? No, right? You are hesitated. So that's good actually. So hesitation is very important, and it's exactly why where AI runs matter. So today we are going to talk about on-device AI, privacy, performance, and real-world edge systems. So I'm Vineeth Gupta, and I work as a machine learning engineer at HP. So I'm also I'm a USF CA grad, alumni, and also I have completed my bachelor's from IIT Madras. So let's talk about privacy. The first word, privacy. So how many of you think we share more than we realize? Like, how many of you think that? Do you all align with me? We share more than we realize, right? Let's see what type of data that we share, right? So personal problems, mental health, relationships, conflicts, etc. Work data, documents, some code, internal strategy, sometimes pitch deck, etc. Identifier, sometimes you go to some place and you ask AI to create an itinerary and some location preferences, things like that. So basically what you're doing, you're kind of giving an AI an opportunity to create a digital footprint of you. So what is the issue? The issue is that AI doesn't fully know what is private. So basically, it only sees the information that you have given. It doesn't know what is private, it doesn't know what is non-private and all. So, so let's see a video, short video.
Harvard students.
I don't know how many of you have seen this video, so
Artifio and Anfu Nguyen say they created this viral video
Is your address?
to sound the alarm over artificial intelligence and privacy.
We built glasses that let you identify anybody on the street.
The two took a pair of so-called smart glasses which have a built-in camera. Practically undetectable, it's activated with a button or voice command. The glasses can capture photos or videos, and with artificial intelligence developed by the students, learn a lot from a face. I'm scared. Scouring internet databases, the AI often able to connect a face to a name, job, interest, even a home address. The information sent almost instantly straight to the user's phone.
June Lee, right?
Oh, is this a warning?
I think so. Yeah.
The tech students say that the budget was $400 and was coded in a matter of days. Two students, albeit Harvard students, were able to do this in 4 days.
Yeah.
What does that say?
All of the technology is already in place, and it's more just a matter of effort into making it exist.
Realizing the potential dangers, Kane and Anfu say they never intended to make their mobile app public, so they led some of the code labs, but they showed us its power using a laptop.
Oh, Aaron McLaughlin, journalism and media appearances. You're involved in writing. Television personality on the Today Show and NBC News Daily.
You can learn about hundreds of millions of people by just looking at them.
Someone walking down the street is just choosing to walk down the street, and now all of a sudden their identity could be known.
Yeah, this is what we wanted to let people know.
The pair's next project, hiding in plain sight.
And then we're creating a wearable necklace with a camera on it.
Oh my gosh, that's cool. The necklace camera and AI scans people's faces and connects the wearer with profiles other users create and willingly share.
And we built it ourselves.
You built that yourself?
Yeah, I do think like the world is very lonely today. People don't really go up to people or like talk to people or learn about others in real life anymore. And I think some in real life like social network could change this.
Their hope that their tech will bring people together voluntarily. Aaron McLaughlin, NBC News, Cambridge, Massachusetts.
So there are some advantages of having these kind of systems to connect better and things like that. But you see the potential risk, right? Like without your permission, a person taking your photo, they have built a system. So this image is passed through that system, and they identify this image, find similar images, crawl through the internet to identify the details about the person, and give all the details to the AI, and AI gives a summarized information back to the user. So that is what is happening in the background. But if you see here, this data is about an individual is already available on the internet. So whatever they are doing is aggregation of the data. So now, so what type of data that you need to worry about? So do you need to worry about any data that is going into the cloud? Maybe yes, maybe no. Why? Because like the data that is already in the cloud, right? Like you use a lot of cloud services, iCloud, Google Cloud, and a lot of cloud services, and you share your photos onto that. Private information like some documents related to you to the cloud. But are there things that we have to worry about data privacy? Maybe no, because when you're uploading the data to the cloud, especially cloud services, something like Google Cloud or iCloud, they pass through several layers of checks. Sometimes could be like encryption, IAM, basically access management, and you have network security, secure containers, and several layers of information and checks that has to be passed through. So basically, this data that you are sending to the cloud is safe when you are uploading the documents to cloud, Google Cloud, or any kind of cloud services, reputed. So data cannot be taken from the cloud because of this high intense architecture about the data security and privacy. But what can be taken? The data that you are sharing with AI can be taken and used in a ways we don't know. So they could use to build a profile about us, or they could use the data to build a system that designs our next actions, things like that. So these are the data that we need to worry about. So now we saw the issues. So are there any regulations, right? Like it's a common question. So we know that the data that we are sending is very private and things like that to the AI. But are there any regulations that are in place? What is the government doing? What is the institutions doing and all? So yes, the institutions are doing something. So these are the two prominent regulation agencies, and each country has their own regulation agencies. So GDPR is an EU law. So basically, governance, data protection, and privacy for the EU citizens. And CCPA is a Californian law. Basically, it enables consumer to know what the business's data using the user data. And if the user is requesting for deletion, the business has to follow that. But these are good. These regulations are good. Many companies follow, but there is one more thing. Some companies, what they do is that they make this process so tough, somewhere bottom of the page, where it's hard to navigate or not. So if the user wanted to delete his personal information, the user has to do a lot of Google search or ChatGPT search to identify what's the correct path to identify and delete the information. So basically, that is the reason these could not be enough, and there could be several reasons, like AI advances much faster than these regulations. So by the time this regulation comes in, there will be already huge amounts of information that is taken by the companies through AI of the user data. So what is the solution, right? So we understood that the data we have is going to the cloud through AI, right? So could the solution be like if the data of you never leaves the device, basically it never goes to the cloud and it stays in the device? Yes, that could be a solution, but there are a lot of complexities. If you look at the frontier large language models like GPT-5, Grok 4, Gemini, Cloud, so it's like each of the parameters, each of the model has around, GPT has greater than 2 trillion parameters, Grok has 1.7 trillion parameters, Gemini greater than 1 trillion parameters, Cloud same too. So, by the way, these are not official numbers. Usually companies don't reveal the official numbers. These are the estimation as per the developers and experts. So, so these are really very huge models, right? Like it's a trillion parameter model. So what's needed to serve this kind of huge trillion parameter model? So it's like, there is a simple calculation to calculate how much memory is needed to host or to serve a large language model as this is. So, so it's basically parameters times you multiply the precision. So I believe in machine learning, I think you all are aware of this. So in machine learning models and AI models, we have something called as weights, right? So the weight precision is what FP32, FP16, Int8, Int4 is. So higher the precision, higher the accuracy. It's like that. We'll talk about it more. But usually, basically, when we call full precision, it's basically 4 bit, 4 basically. If it is half precision, 2, something like that. So let's say if we have 1 trillion parameter model with floating point 32-bit precision, we basically need 4,000 GB of RAM. It's basically 40. It's very huge, right? So if we take this example, this is an NVIDIA A100 80 GB GPU. We need 50 A100 80 GB GPUs like this to host one single frontier large language model. And if we imagine like how big it is, it's like a data center. So basically, the minimum would be around 200 square feet. So this is a simple setup. There will be coolants, there will be a lot of engineering, hardware engineering aspects there, but this is the bare minimum. So if you look at model sizes, so frontier models are the models which are like greater than 100 billion parameters. We have large language models, which are like 30 to 70 billion parameters. And these are small to medium language models. We have 7 to 13 billion parameters. Small language models, 0 to 0.5 to 7 billion parameters. And tiny models, which are less than 0.5 billion parameters. Again, these are not exact distinguishments. There is no proper way to distinguish this parameter size is definitely small language model, this parameter size is definitely large language models. These are the general industrial norms that usually people follow. So let's talk about small language models. We understood that frontier models need a huge data center and huge setup, and that will not be possible. We have a device like this in hand and a device like this in our hands. So, so let's talk about small language models. Why? Because only those kind of laptops, those kind of language models can be fit in laptops and edge devices. So common techniques to create small language models. So there are various techniques to create small language models. One is architecture slimming. So we design this huge large language models. They have this complex architectures of multi-head attentions, flash attentions, and huge memory consumptions, and things like that. So you know this, there are several layers, like huge amount of layers. During the design itself, instead of creating the huge architecture of layers, compress it, like design a smaller, smaller model by shrinking the size of the architecture. But can it perform as good as the large language model if you just shrink the model layers? The answer could be no, because it's kind of, you're basically, the complex information that the huge large language model is learning cannot be transferred or cannot be learned in the same way when you have small language models with shorter layers. So one is like knowledge distillation, pruning, and quantization. These are the few techniques of creating this small language models. And each of the technique is very complex. Like people do PhDs on each and every topic. So if you see, there could be like every now and then there is some new knowledge distillation technique, some of the other new pruning technique, some of the other new quantization technique. So we are not gonna do that level of complexity, but I'll try to introduce you to some concepts and get you familiarized with these concepts. So knowledge distillation. How many of you have heard about this knowledge distillation? Have you guys heard about this knowledge distillation? Yeah. So to understand this large language models to small language models, that would be kind of complicated. So I took this deep learning approach to show you what this knowledge distillation is. We have the training data. We have the large model, which is a pre-trained model, and we have a short model, which is like student model. So what we are doing is we are using the pre-trained model, large model as a teacher, and we are using short model as a student. So what we are doing is we are training the student model in such a way that it has two things, three things basically. It has input data, labels, basically the ground truth. Along with that, we are also giving predictions, basically the soft probabilities from the teacher model. So usually what we do, whenever we are building machine learning or deep learning model, what we do is that we give only two parameters, right? Input data and the labels. So here we are giving additional parameters called as soft labels. What we are doing, what we are trying to achieve is that the student model will try to fit the parameters by training through the, basically it's trying to bridge the gap between the training data and the labels. Also, if you give the soft labels of the teacher model, basically what it does is it tries to learn the pattern of the teacher model, and it tries to replicate that type of architecture or that type of learning structure through the soft levels. But here we have a different loss function. So we have cross entropy loss. You guys know cross entropy loss, right? Binary cross entropy for classification. And we have this component over here, and this component is like KL divergence. So basically we have two probability distributions. One is from the pre-trained teacher model, and the one is from student model. So this KL divergence kind of compares the probability distributions of basically the two probability distributions. So basically we have two parameters, temperature and alpha. How many of you know temperature parameter? Do you mind explaining about the temperature parameter? Anybody? Yeah?
I believe temperature in LLMs is essentially like how wild the LLM is allowed to be, since it's just predicting like the most likely word. It's how almost unpredictable it's allowed to be.
Yeah.
I believe is what temperature is.
Yeah.
So like a low temperature means it's probably going to predict the same word given the same prompt, versus a higher temperature means it could answer a lot more creatively.
Yeah. So basically, if temperature is lower, you're making the model narrower, predictions narrower. But if your temperature is much higher, then basically you are expanding your scope. What it actually means? Do you know what happens in the background? This was an interview question that was asked to me. So when you change the temperature parameter, what's happening in the background? Anybody of you know what exactly is happening? Yeah? Where does the noise get added? Yeah?
I believe, I read it in a book. I believe what they said is that they like artificially lower the probability of the more common words,
Yeah.
so that therefore it's more likely to predict more uncommon words.
Yeah, you're in a way right, but where exactly is happening? Where is it happening? Okay, I'll tell you the answer. It would be helpful for your interviews. So, so we have the softmax function, right? Do you know what does the softmax function do? Yeah.
Make probabilities add to 1.
Yeah. Basically, it kinds of do a computation about the probabilities around the labels. So, anybody know? I think you all know softmax function. Okay, so we have the function like e power k by sigma e power k, right? So when you add probability, what happens is that like the softmax function would be changed. So how it changes is that the softmax, when temperature is added, it would be e power k by t, exponential power k by t, by sigma exponential e power k by t. So basically, that's where the temperature parameter is getting added, and that's how the probabilities are kind of smoothened, right? So remember, if you get asked this question in the interviews. So there is another technique called as pruning technique. So we have huge architecture where the weights are interconnected. So what we usually do is that we disconnect the neurons that are not, or disconnect the layers or weights that are not significantly contributing to the predictions, right? So what are the common types? So one is unstructured pruning. So remove individual weights. This is called as unstructured pruning. And there is another approach called structure pruning. So what we do is that we remove the whole layers or heads in the attention layers that are not contributing significantly to the predictions. This is better for hardwares. So if you have a bigger model and if you wanted to have it on any kind of limited hardware resources, so maybe you can consider structure pruning. And quantization. How many of you have heard about this word quantization? Anybody heard? Yeah, good. Nice. So what basically quantization is? Like we discussed, right? Like each of the deep learning or machine learning model has some weights, and weights has some precision. So we discussed about FP32, 16, and things like that. So if you look at this example, right, we have 6.66 as the value. So what we do is that to store that particular value, we need we need not this in this example, but we need some memory, additional memory to save that floating point. So what we do is that we quantize this neural network weights and make it integers. Basically, we are converting float to integer value. So since it is single integer value, it's much lighter to hold it onto the memory. So you know this this value. What is this value? Pi, right? So so computer scientists remember the whole series up to some number. So this is a famous meme. So applied mathematician remembers only to certain value, while engineers like us remember only the integer values, right? So basically, this is what we are doing quantization. So we are trying to shrink the parameter value by some a limited value so that we can remember. So remember as in the memory. So these are the distributions. Like we have FP32. So basically, it's 32 bits, and it requires high memory, huge memory load, and the precision will be very high. So when you are making any prediction during the training and during the inference, if the model is having high precision, basically FP32, then that is the max precision that you get, accuracy that you get. So when you use this, it's for stable training basically, but there is some issue. The thing is that it takes a lot of time to train because very huge values, right? So it takes a lot of time. So there are other data types, FP16 and BF16. So FP16 and BF16 are called as half precision. So they consume like 16 bits. The memory is not as much as full precision, but medium. And precision, there is some compromise on precision as well. So because we are cutting down the values. So, but if you compare the speed with full precision, it's kind of fast. So when do you use it? You use it when for training and inference. FP16, int8, int4. These are the common most quantized models for edge devices. So the memory that would require would be low to very low, and since we are quantizing such a big value to a integer set of values, so the precision would be very low, basically medium to low, much less to medium basically. So but the inference will be much faster. So the computation during the inference point would be much faster when it's passing the activations through several layers. So where this is used, right? Like int8 and int4 is predominantly used in edge systems, basically some limited hardware resources, servers and edge devices. And when you wanted to use a large language model, then you use 4-bit quantization to make it small and host it on the device. So there are various techniques in quantization. First thing is like post-training quantization. So as the name suggests, the quantization is applied after the model is trained. So during the training, we use the full precision. We train the model with based on the setting, full precision or half precision. But once the model is trained, during the inference, we quantize it. So what are the advantages of it? It's like the advantage is like fast. The inference is much faster when you quantize it. No training is required. Since you are just shrinking the values of the weights, you don't need to do additional step, and it's easy to apply, simpler. But the disadvantage is that it quickly drops in accuracy. You see a big drop in accuracy. Alternatively, we have context-aware quantization. So what we do is that in the whole neural network architecture, what we do is that we add fake quantization operations. So what happens is like, So before, why it is performing bad? Because there is some information loss, right? When you are quantizing the weights. But now what we are doing is we are adding fake quantization operations. Now what's happening? You are basically adding some layers where they will mimic the quantization technique. So basically there are two steps, quantization and dequantization. So that particular loss when you are quantizing the weights is digested through the loss and updated during the backpropagation. So the model will kind of expect, okay, there is some quantization technique that's happening, and that kind of loss is already absorbed in the model. So what is the advantages? Advantages are like best accuracy, since the loss is already captured into the model, and the models are updated as per the architecture. It will be updated. So stable even at int 8 and int 4. Directly quantizing the FP32 or FP16 drops the performance. But since you are adding fake quantization, it helps you in basically when you basically during the training process you have these fake operations, quantization operations. But when you are inferencing it, what you do is that you remove the full precision values and make it quantized, right? So that's why it would be much stable in int 8 and int 4 configurations, but expensive. Expensive because you need to do again training, again memory requirements and all. So just by this, could someone say when do we use post-training quantization and context-aware quantization? So post-training quantization is usually used when you don't want to handle a lot of memory, or when you don't have training resources, things like that, and when you wanted to quickly host the model onto the server or onto their edge devices. That's when you do post-training quantization. And context-aware, basically that's the opposite. So when you have some resources to train, then you use and when you want the model to be precise or accurate, you don't want to drop in performance, that's when you use context-aware quantization. So till now, you guys have any doubts regarding quantization, knowledge distillation, pruning? Feel free to have raise your hands and ask the doubts if you have. So comparison. So now we talked about 3 different types of techniques to create these small language models: distillation, pruning, quantization. So basically what each of the approach does. Distillation reduces the capacity and basically the behavior. So since you are kind of reducing the architecture from big architecture to small architecture, the capacity of the model to reason the complex, basically the complex reasoning capabilities would be reduced. When you use pruning, so basically this is an advantage. What's happening is that you are reducing the redundant weights, and then when you use quantization, basically you are reducing the precision. Precision, because like FP32 to int4 or int8, it's like a huge drop in precision. That's what you're losing. What about speed, right? Latency. Have you heard about the word latency? Right? Speed, latency, right? So latency, when you use distillation, there will be low to medium impact, depending upon the size of the architecture you're choosing for student model. Pruning is like medium, because it also depends upon the parameter, like how many neurons or how many layers that you are kind of cutting out. And quantization, it's really fast. It's really, really fast. So if time permits, we'll try some on this experimentation. I'll show you like how to host an LLM locally. So there are a lot of frameworks that helps you run the model on the devices. One is Olama, LM Studio, and Llama CPP. These are the three prominent, or there are much more than this, but these are the three most user-friendly or developer-friendly environments to run the models locally. So, what are the advantages of on-device AI? So, privacy. So that no data is going out of your device, since the model is LLM model is or AI model is on device. You are interacting with the AI, and no data is exchanged through the cloud. Cost. So, how many of you agree with this point called as cost? Right? Yeah. You have anything to ask? So, why cost? Like, so a lot of companies now are doing a lot of inferences, and companies are spending like millions of dollars just for using cloud LLMs. Basically, the cost is a huge factor when you are running the model or calling the model. So whenever during the interviews as well, like when you are designing an architecture, sometimes they might ask you what would be the cost, like how expensive is to host this architecture, system designer basically. So latency. So when you have latency, what are the advantages of having on device, right? Like if you have the AI model on device, the response would be much quicker because there are no gateway interactions. There is no internet connectivity requirement. So completely local. That's why the latency will be much lower. So no dependency on network framework. So if you don't have internet, it's fine. If you don't have Wi-Fi, it's fine. So yeah. So challenges. So all good. On-device AI sounds good. Everything. Is it easy? Very tough. Why? Because resource and performance limits. So we know that AI models are really very huge. So even if you shrink the model to in 4-bit quantization, when you host the model on laptops, it's running on the laptop. Basically, it's taking, it's having some memory footprint, it's taking some CPU, it's taking some GPU. More importantly, it's taking some battery as well. So the huge computation runs on your device that causes huge performance limitations and model size and quality constraints. So the model size are good, like they are short, but if you want to make the model perform really well, if you want the model to have reasoning capabilities, like complex reasoning capabilities, that could not be possible because of the size of the models. And deployment challenges. Why deployment challenges is that we have huge various kinds of architectures, hardware architectures. If you look at GPU, there are wide range of companies, right? Like NVIDIA, AMD, a lot of companies like that. So if you have developed one framework to host a model on the edge device, that may work on NVIDIA GPUs, that might not work on AMD GPUs. So AMD GPUs, NVIDIA GPUs are again, there are wide range of types of GPUs that they provide. So these are the deployment challenges. So it's very tough to deploy an AI model. So now that we understood about the advantages, the disadvantages, the challenges, the complexities, the types of frameworks, the various ways to create small language models, let's look at real world edge systems. How many of you have drove or sat in Tesla cars or Waymos? Right? Have you ever got fascinated when you see the FSD, full self-driving? Right? So when I first came to US, I was sitting in Tesla and I was like very excited. So how is it driving by itself? That curiosity was very interesting. In fact, that was the first visual confirmation that AI is making a great impact, right? On the roads. It's a visual impact. AI is applied onto the hardware and it's doing the job. So we have self-driving cars, Tesla, Waymo and all. So for Tesla, again, we have a huge set of computer installed on the car, in the car basically, in front of dashboard, so behind the glove box. So the AI models runs on this GPU and it controls a lot of parameters like amount of rotation that steering has to do, and when to honk, when to turn on lights, things like that, lane detection and etc. It's very complex architecture. In fact, there is very limited amount of information to kind of learn what Tesla FSD is doing. It's like kind of IP for them. But if you even approximate the architecture, it's really huge. That takes a whole session to teach. And there is, how many of you believe in robots? So what do you mean by believe? Like, do you think robots are gonna take over? Huh? Maybe. Yeah. So one of the huge limitations about this robotics is that it uses complex AI models, right? The AI models are hosted onto the some server, and these robotics or robots, what happens is that they pass the information through the server, and the server computes it and sends it back through the action. So the Google Gemini model, vision language model, language to action model, basically. The before model to this was hosted onto the server, but when they connected the whole architecture and integrated with the hardware, there was a lot of latency. What used to happen was whenever have you seen robot videos where it's taking very slow steps, very slow actions, things like that, right? One is due to the motor that it has, the electric and mechanical limitations, and the other thing is that it's due to the decisions. So that the decision has to come from the server. So Google Gemini robotics team has identified this issue and kind of developed an on-device model. Now this model runs on the memory chip or the computer on the robot, in the robot basically, and it helps us in taking decisions much faster. So basically, it can put the white t-shirts in the gift box or gift bag, and then stress ball as a gift bag, and things like that. So basically, it does a lot of activities. So I spoke about a lot of on-device AI and things like that, and some may have curiosity to know what's happening on in my workspace, what is HP is doing about related to AI. So we have something called as AI Companion. We used the frameworks. One of the frameworks that I was talking about some time back, the framework, Olama, Llama CPP, and things like that. So we are using one of the frameworks, prominent framework, to host the AI model onto the device, and we build the software around it. So the users of HP can upload their documents to the AI Companion, and it summarizes the documents, same as ChatGPT or any AI cloud AI, and it also provides actionable insights. There is also called as something called as Perform tab. So what happens is that you can control your PC with voice. For example, if you ask it to increase the brightness of the screen, it does the job. Or if you want to increase the volume of the speaker, it does the job. For example, it also does some, there are also some challenges. For example, if you say increase the volume to, output volume to, let's say 60%, and then you say, oh, that's too much, reduce it to 40%, or reduce it by 10%. So you see the complexity, right? You have to say what is the previous action and what is the current action, and reconfigure the new action. So this is about AI companion, and there is something called as HP's poly segment. So there is something called as director AI. So what happens is that you have conferences, and you have this huge speaker and camera boxes. So what happens is that, like, when you are in a conference and when you are talking, when there are a group of people, that AI intelligently detects who is talking, what are the faces, what are the who are the people, and basically tracks their faces. And for example, if someone is speaking, they focus more on the on that particular speaker. And there is Camera Pro. Basically, we have HP webcams and also external webcams as well. So we have this on-device frameworks to enhance the video quality and better processing. So yeah, thank you. I hope you like the session.
Does anybody have any questions?
Feel free to ask me questions. Yeah.
Kind of curious how, like, what the gap is between this program and a machine learning engineer role. Like, is there self-study within there, or is it like something you can apply for straight out?
Yeah, you have to do a lot of self-study, to be honest. So I think, like, some things are will be covered for you. So I think there will be some LLM courses in the summer. So there will be some concepts covered for you, quantization, things like that. But now you have to also build up over it. Like, you need to learn a lot, various types to be interview ready. So yeah, and I think over the time, many people will start contributing to on-device AI, and there will be more opportunities. Yeah.
Do you think that further progress in terms of what kind of AI we can run on the edge, do you think that's going to be improvements to the hardware or to software? Like some more compact software, or just hardware that can hold more memory and data?
Yeah. So the question is like, so when you host the model onto the AI model onto the devices, is it going to be a software enhancement or a hardware enhancement, right? So that's the question, and the answer is both. You need software enhancement and also the hardware enhancement. So if you see, like, Apple has launched A16 chips that are capable of handling or hosting AI models compared to the previous chip, A15. So any company, any hardware company is trying to make the chips much compact and much capable to hold the models. So also the softwares as well, like we are talking about the techniques that also are getting updated, and that also getting transformations, a lot of transformations. So I just give the introduction of various techniques, but there are really big, very complex architectures that people are trying out there. So both. Yeah.
What resources do you use to stay up to date with things developing in the tech industry?
So, yeah, I mean, there is no straightforward. I follow a lot of articles. So when it comes to what's happening in terms of the LLM space, I follow this OpenAI's Anthropic and blog posts. Along with that, if all of a sudden, right, like all of a sudden you hear some flashy name called as flash attention. So all of a sudden someone will be talking about that flash attention, and that, how many of you heard about something like MCP, model condition? So all of a sudden you hear that kind of terminologies, and then you get the curiosity, then you go through the article, researches, and you read research papers. So it's kind of both intentional and unintentional knowledge that you give. So yeah, if you want to keep up with what's happening, maybe follow the tech companies, AA blogs, Metas, and there is huge open source work that is going on. So maybe if the tech companies are not not posting any information about the models that they have, there are a lot of open source contributors that are working on and similar things and releasing them. So how many of you know this all this open source models? You all know, right? So closed sources like the large models, Gemini, OpenAI, basically GPT, ChatGPT, cloud and all. But there are open models as well. How many of you have heard DeepMind? Google DeepMind. So that works on Gemini and a lot of things. But DeepSeek, when you have a nice. So all these models. So yeah. Any more questions? Yeah.
Is there, can you tell us anything about what devices you currently are working with or recently worked with?
So yeah, I mean, HP has a lot of segments. So we have laptops. There is a huge growth in a segment called as AAPCs. So AAPC is a segment. So we have CPUs, we have GPUs, and we have something called as NPUs. So these NPUs handle are specifically designed to have AI models on the edge. So when you run this AI models, if you have NPUs, the NPUs take care of the job. So edge devices like headsets, camera systems, these two comes under Poly, and the AAPCs that HP has. I hope I answered your question, but I can't talk more about it. So yeah. Anything else?
All right. Thank you so much.
Thank you.
Thank you all for listening and showing the